You have been likely told since you were quite young that the reason why materials hold together or cohere is because there are these intermolecular bonds or attractive forces between the atoms that comprise those substances. What I want you to do is to put aside for the moment all the things you've been told by your teachers, at least regarding atomism and atomic bonds, and to think afresh about why it is that things cohere or hold together. After all, that is precisely what Galileo is wrestling with in this day one of his dialogues concerning two new sciences. You might recall in the past two lectures, we were talking about Galileo's analysis of why it is that a column of water can only be drawn up to about 18 cubics or 30 feet in a tube using a plunger, drawing the water up. It can only go up to a height of about 18 cubits, 30 feet, before the column of water breaks. That is, the plunger with which you're drawing it up separates from the surface of the water. The plunger continues to ascend, but the water remains at about 18 cubics or 30 feet high. Above this water level, there's a vacuum that is formed. So what Galileo is trying to do here is he's trying to demonstrate that while nature abhors a vacuum, this is the theory that he had inherited from the older scientists, while nature abhors a vacuum, it really only abhors it with a certain strength. If there's a column of water more than 30 feet tall, it weighs enough to create a vacuum at the top of it when you try to lift it up into a tube. So nature's abhorrence of a vacuum is limited. And then he goes on to talk about how if you were to do the same thing, but instead of drawing water up into a tube, you were to take a coil of copper wire, grab the end of it, and begin to lift it. This copper wire holds together until at least you get it to a height of about 4,801 cubits. That is over a mile long. That copper wire will hold together. And what Galileo argued was that you would only anticipate, because of the density and hence the weight of this copper wire, you would only anticipate that you could lift it to about a height of 2 cubits before it broke under its own weight, if nature's abhorrence or hatred of a vacuum were to account for the cohesion. But of course, the copper wire can go much higher than this, 4,800 cubits, so something else must account for the cohesion of the copper. Perhaps, Galileo suggests, there are some kind of internal forces within the copper that are holding the parts of it together, some kind of internal bonding. And one of the ideas that Galileo has is that maybe there's some kind of gluey substance that's holding the little parts of the copper together. So that's one of the first thoughts that Galileo has to account for this. But Galileo actually doesn't run with that. What he suggests is, instead of some gluey bonds holding the parts of copper together, maybe there are tiny vacua in between each of the little parts of copper that make up the wire, and these tiny, tiny vacua that are interspersed throughout the copper could account for this internal bonding of the copper. This raises the question, you can kind of see where he's going. You see that he's starting with this macroscopic, large-scale problem, and he's very quickly led to asking questions about the structure, the internal structure, and in fact the microscopic structure of material. So you see kind of the birth of a careful analysis that leads to atomism here in the work of Galileo. Now, here's a question. Is it possible to have these tiny, many, or perhaps countless invisible gaps inside of a substance? And that's a question that Galileo now turns to. Is it possible to build up some material out of a whole bunch of parcels of the material, which are among which there are these many tiny gaps? And so this is what Galileo is going to be arguing for, but how does he make this argument? How does he justify this perspective? And so this is where he starts talking about Aristotle's wheel. So let me turn off my webcam and give you a short introduction to Aristotle's wheel, and then we'll bring this back around and explain what this has to do with the existence of tiny gaps or vacua within a material and Galileo's theory of atomism. Okay, so this is on page 21 of the text. Actually, it starts on a previous page, but you'll see here, this is Galileo's discussion of Aristotle's wheel. Before we talk about this diagram, let me give you a short introduction to Aristotle's wheel. Aristotle's wheel. This is a very interesting topic. And this is right around page 21 of a student's guide. This, by the way, it's called Aristotle's wheel because it appears in a work that was attributed to Aristotle called his Mechanica, or his Mechanics. The Mechanica of Aristotle, he discusses this problem. Here's the root of the issue. Aristotle says, let's suppose you have a wheel, okay, and you put a mark on it on the bottom. Let's do a red mark. And let's suppose furthermore that this wheel has a radius of capital R. Okay, so that's the radius of the wheel. And if this wheel were to roll along the ground, as it rolls along the ground, eventually it gets back to a point where that dot that was on the bottom is once again at the bottom. So it rolls around one complete time. Okay, so here you might imagine a wheel. You maybe paint this orange line. You let it roll around once and it gets back to the same point. And the question is, how long is this line that it traces out? Well, it's a relationship, you probably know, between the radius of the wheel and the circumference of the wheel. It traces out the entire circumference of the wheel. And this would be 2 pi times the radius, or pi times the diameter. 2 pi times the radius, or pi times the diameter. That's the length of this line segment. Okay, good so far? Now let's suppose that you were to take another wheel, and this one's a little bit smaller wheel, with a different radius. We'll call this little radius little r. I'm going to draw it out here so you can see it. And let's suppose, once again, you roll this wheel so that it goes all the way around one time. And so this spoke or this line lines up back where it was. And so when it rolls, of course, the length that this draws out will be 2 pi times little radius, or pi times the little diameter, right? No problem so far. Okay, now here is the paradox that is brought up. Let's suppose, says Galileo, that you were to take this big wheel and you were to glue the little wheel to it right on the axle. So you've got this radius little r on that wheel and the radius big R here on the big wheel, okay? And you were to set this on the ground and you were to roll this big wheel so that it goes around exactly one time. So again, I'll draw this big wheel right here. So once again, this big wheel is rolled around one time. And when you do that, well, I'm gonna suggestively, I'll do this with a different color this time. Of course, the ground, it rolls along the ground a distance equal to 2 pi times that radius r, right? Just like up here. Now the question is, this little wheel also rolls around one entire time. So I'm just drawing a line here indicating the distance along which it rolls. It rolls around one time because after all, it is fixed to this big wheel. You might think about it as being either glued or bolted to it. So if the big wheel goes around once, so too must the small wheel. And it ends up in the exact same position it was before. And here's the perplexing part. What is the length of this line segment? Well, it's got to be the exact same length as this line segment down here. How is it now, and this is the paradox, how is it that this little wheel rolls around exactly one time, just like the big wheel, and yet it traces out a line segment that is equal in length to the circumference of the big wheel? This is called Aristotle's paradox. Aristotle's wheel paradox. This is Aristotle's wheel paradox. By the way, there's a very interesting discussion about this. Let me just give you a reference here. Aristotle's wheel. Notes on the history of a paradox. This is an article. Notes on the history of a paradox. And that's the title of the article. I don't recall what journal it's from. I have a copy of this, but it's by an author named Israel Drabkin. It's a fascinating discussion of this that's going to go into much more depth than I do here. So the problem again is that as this wheel rolls, the outer and the inner circles both trace out the same circumference. How is this? Does the inner wheel slide after all? Well, if it doesn't slide, are the same number of points that comprise the inner and the outer wheel. Aristotle's wheel caused a great deal of discussion and consternation because it raised questions about how to think about bodies and continuous bodies and whether you can construct them out of points and how many points it takes to construct them. Specifically, is it possible to build a finite-sized object, such as a line, by adding together points? And here's the puzzle. A point is technically a zero-sized object. How can you add together a bunch of zero-sized objects to construct an object of finite size? More specifically, do geometrical points, in fact, exist? So this really gets to this question of how should we think about space and objects filling space? Are they comprised of points, or are points merely abstractions? And this really is something that people were trying to deal with when talking about atomism. And this is why this comes up in Galileo's text. The way that Galileo approaches this is he says, let's not think about a rolling circle, and this is now looking at page 21. Let's not think about a rolling circle. Let's think about a rolling polygon. And you can see in his figure 2.2, you have a six-sided polygon, A, B, C, D, E, F, and inside of it, a smaller polygon, HIKLMN. And what you do is you roll this polygon, and as you roll it around one time, the line segment A, B, Q, X, all the way over to S is traced as that polygon kind of flops over and rolls around one time. And the circumference, so to speak, that is that line segment, is comprised of the entire perimeter of the polygon. The little polygon, however, as you're rolling it, the little polygon kind of lifts up and then falls back down. So the line segment IK on the little polygon, as it rolls along, it lifts up and it lands down in line segment OP. So you get this gap IO where there is not a line segment. And then as it continues to roll along, it kind of hops up and lands down, the sides KL going to points YZ and so on. So this rolling polygon, the bottom line ABQXS is a continuous line, whereas the smaller polygon, as it rolls along, goes along HIOPYZ, but there are line segments interspersed with gaps. And then what Galileo does is he says, if you take the number of sides as it approaches infinity, from 6 to 7 to 8 to 100 to 1,000, the number of line segments and the number of gaps gets larger and larger and larger. And eventually you have an infinite number when you get to a circle as a limit of polygons of many, in fact, an infinite number of sides. This line segment HI up to T is comprised of an infinite number of points separated by an infinite number of gaps. And this is how Galileo is thinking about materials. His view of atomism is that materials, such as copper, are really comprised of an infinite number of infinitesimally small atoms that are separated by an infinite number of infinitesimally small gaps. And these small gaps, he would argue, are tiny vacua. And these vacua, when added all together, are able to account for the internal cohesion of substances. So this is how, when talking about the cohesion of substances, the discussion in Galileo's dialogue quickly turns to the microscopic nature of materials, and the idea of atomism. I want to say one other thing about atomism before we go on. You'll notice that in the text, at one point, Salviati, who is describing this view, is criticized by Simplicio. I think it's Simplicio or Sagredo. It's in the next couple of pages. They insinuate that he is being unfaithful or perhaps heretical by pushing for this atomistic viewpoint. In fact, Galileo's endorsement of atomism was in fact somewhat theologically suspect at the time. Why was it? Well, because atomism was, there are a couple of reasons. First of all, because atomism was notoriously associated with certain pagan philosophers, most notably Democritus and Epicurus. So if you were an atomist, then you were associated, at least to some extent, with these pagan philosophers. So that's one reason why he was being given somewhat of a hard time about this. Also, and perhaps this is the more important issue, and we'll talk more about this later on in the semester, but atomism, the perspective of atomism is that the atom is the fundamental unit out of which all things are made. And if you just understand the configuration of atoms in a substance, then you have completely understood what that substance is. There's no need to appeal to anything else if you're a strict atomist. And the problem is that this seemed to contradict the doctrine of transubstantiation. And like I said, we'll talk more about this later, but some of you have probably heard of this term transubstantiation, having to do with what happens during the Lord's Supper or communion or the Eucharist. And why was this a problem? Well, because in transubstantiation, the view was that the bread that one is eating during communion actually turns into the body of Christ, and the blood and the wine turns into the blood of Christ. Now here's the problem. If atomism is true, and if what something is can be completely described by the atomic configuration, then before the priest blesses the bread, the atomic configuration of the bread is just that of bread. And after the priest blesses the bread, the atomic configuration is still the same. And if it is still the same, the bread is still just bread. After all, it's completely determined by the atomic configuration. And if the bread is still the same bread, it is not the body of Christ, and so this seems to fly in the face of this doctrine of transubstantiation. So you can see how these scientific theories end up having a bearing on theological discussions, and theological discussions have a bearing on these scientific theories. This is a very interesting topic of discussion. It'd be fun to talk more about this, but I should probably end our discussion of this now, and I will talk to you next time.